Hello everybody to our short and fast-paced refresher for linear algebra. Short and fast-paced because I assume that you know most of the material. If you don't know linear algebra basics, please consider some standard textbooks. So the material here is based on slides from David Barber, who is actually a very nice book of machine learning, Bayesian reasoning and machine learning, where you can get a little bit more details on math background if you lack those. Okay, so linear algebra, the main objects of linear algebra are actually matrices and vectors. So a matrix is a very simple object. It's a rectangular collection of scalar values. It has m rows and n columns, and we often denote the element at position ij by matrix aij, or sometimes by those small scalar aij. And the first operation is addition on two matrices, and it's simply done component-wise. The next operation is multiplication between two matrices. It's a little bit more involved than simple addition. So the product A, B only exists if the two matrices fit. And what does it mean? They fit, well, matrix A is L by N, and the matrix B that's supposed to be multiplied by the right side to A has to be N by M. So those two numbers have to fit. So if they fit, the multiplication is simply defined as this row and this column produce the first entry of the new matrix, and so on and so forth. Note that matrix multiplication is not cumulative, so BA is usually not AB. A very simple matrix is the identity matrix, which is simply the matrix with ones on its diagonals and zeros everywhere else. The transpose of a matrix is simply switching rows and columns. So the kjth element of B transposed is simply the jkth element of B. And now see, if you transpose twice, you get B back. And here's an interesting relation. If you transpose the multiplication between A and B, it's B transposed times A transposed. And similarly, if you have an expression like that with three matrices, they transform like that, and you can scale this up to arbitrary numbers of matrices. So vectors. Vector is simply an n-dimensional column of a matrix, for example. So we stack numbers as a column. And addition is again defined component-wise. So this entry plus this entry is the entry of the result vector, and so on and so forth. There is a multiplication defined between two vectors. It's called scalar product, and it's defined like that. Okay, the scalar product between a vector W and X is this summation expression. So you see both vectors have to be of the same length, and often it's written like that. And well, it uses the the transpose sign, which makes sense if we consider that W is actually a matrix of form n by 1, and X is a matrix of form n by 1, then W transpose is a matrix of 1 by n, and then you could actually apply the standard rules of matrix multiplication. The vector X also has a special scalar associated with it its length, and its length is simply the scalar product of x with itself. And then you have this well-known form, and we call the vector x a unit vector if it has length 1. The scalar product itself can also be represented in a geometric way. So the scalar product between w and x is actually the cosine of theta between two vectors w and x times the length of w and the length of x, right? And here the length of x is the square of this, okay? So the concept of linear dependence is a rather important concept for linear algebra. And the idea is that if you have a set of vectors x1 to xn, then they are called linear dependent if there exists a vector setting of alphas such that those weighted sum of the xi's actually produces a 0. If this is not possible, so if the only setting of the alpha i's is equal to 0, then we call those vectors x1 to xn linearly independent. Projections. Actually, the interesting part on this slide is this thing here. So what are we interested in? Assume we have a vector A, and I'm drawing it like this. Okay. So this is A, and I have a vector F, like this. Okay. And now I would like to know the length of A along F. So what I'm actually interested in is what's happening if I'm projecting A onto F. What's this? As it turns out, this is exactly this quantity. So the scalar product between A and F divided by F squared, so the length of F squared times F. So this is a scalar, this is a scalar, this is a scalar, but this is a vector. So this is this F. So this quantity is actually this thing here, the length of A projected onto F. You may think of those terms A scalar product of F and the length of F squared, why they are necessary to produce this length. That's a good exercise. The determinant of a matrix. So assume that we have a matrix A that's 2 by 2, as written here. And what I actually would like to know is what's happening if I apply A to these 4 vertices here of this 2-dimensional cube. How are these 4 vertices transformed by A? Okay, for example, they are transformed like that. Okay, so the cube on the left side is transformed to the cube on the right side. And one thing that's interesting in this transformation is how does the volume from this cube transform to this sheared cube. And this is actually what is measured by the determinant of A. And as you probably know, computing the determinant is rather involved, even though there are a couple of nice recursive formulas, but for big matrices, computing the determinant is usually a difficult task. There are a couple of nice identities. In particular, the determinant of a transposed matrix is actually the determinant of the original matrix, and if you have a product between two matrices A and B and would like to know the determinant of the product, then you can say the determinant of the product is the product of the determinants. The determinant of the identity matrix is 1, and therefore if you have an inverse matrix of A, then the determinant of this inverse matrix is actually simply 1 divided by the determinant of the original matrix. We will talk about the inverse actually a couple of slides later. Oh, actually we talk about it right now. So the matrix inverse of A only exists if A is itself a square matrix. So there's no nice definition of a matrix inverse for non-square matrices. We will see one on the same slide later on, but in general the matrix inverse of A is only defined if A is a square matrix. And what's the definition of the inverse of A is if I multiply the inverse to the left of A or to the right of A, then the result is the identity matrix. And even if a matrix is square, it's usually the case that the inverse does not exist. In case it does exist for A and B, then the matrix A times B has a nice inverse that's actually B inverse times A inverse. This looks rather similar to the rule of the transpose. So for non-square matrix, we can have sort of a pseudo-inverse that's defined if A by A transpose is actually invertible. And this pseudo-inverse is defined like that. And why is it called pseudo-inverse? Well, if you multiply A by A pseudo-inverse, then you get the identity. And this is actually an important formula that we need later on in linear regression. Okay, so the inverse of a matrix is theoretically important if you would like to solve a square linear system. So we have a square matrix A and a vector B and would like to find vector X such that A times X is B. And if this inverse exists, then you can solve this nicely accordingly to this formula, but in practice, of course, we would never do this. Instead, you will use the well-known Gaussian elimination algorithm, which is numerically much more stable. So one thing to remember here is never compute an inverse if you really want to implement algorithms on a computer, because the inverse is a difficult and particularly numerically unstable operation. So algorithmically solving a linear system is in the order of n to the third, which is of course rather expensive for large n. Another characteristic number for a matrix is its rank. So the rank of a matrix is the number of its linearly independent columns, and this is equivalent to the number of its linearly independent rows. And a matrix, a square matrix, is called full rank if its rank is n, if it's n by n. So we already saw the determinant, and the trace of a matrix is a similar number to the determinant. The trace of a square matrix A is the sum of its diagonals. So if a matrix looks like that, then we add up the diagonal elements. And if you know the concept of an eigenvalue of A, then it's actually the sum of its eigenvalues. And interestingly enough, the determinant of a matrix A is the product of its eigenvalues. And the matrix is singular if it has a zero eigenvalue. And you remember, we also called a matrix singular if its determinant is 0. So there is an interesting identity between the trace and the determinant, which is written down here, but we don't need it in this lecture actually. Another word that tries to describe a matrix is the idea of orthogonality. A square matrix A is called orthogonal if its transpose is its inverse. And, well, what does a matrix actually do if it's applied to a vector? Well, if we think about A times X, then it's actually a linear transformation of X. Or, if you look at it from a different perspective, what is doing X, the vector, with the matrix A? Well, as we see here in this equation, the vector X acts on the columns of the matrix A if we multiply it from the right side. So the columns of A are like that. And if you now multiply a vector X from the right, then it actually turns out that something like this is happening, where these lines are the columns of A. And actually, if you write it like that, then this linear transformation actually means that X is acting on the rows of A. So you could try to write this in a form like that, and then you would see that this sum is no longer on the columns, but on the rows of A. So now the concept of eigenvalues and eigenvectors. This only exists for an n by n square matrix, and we say that E is an eigenvector of A with eigenvalue lambda if the following relation is true. So A applied to E results in a scaled version of E. And, well, how do you find eigenvalues and eigenvectors? What you actually have to solve is you have to find all the lambdas such that the determinant of this matrix expression is equal to 0, which leads to the famous problem of finding the roots of the characteristic polynomial of a matrix A. And given that you find these eigenvalues, then you can identify the eigenvectors. And in general, the eigenvalues and the eigenvectors are actually complex numbers. But if you are lucky, and in machine learning you are quite often lucky, then you have a real symmetric matrix A. And this real symmetric matrix A has a spectral decomposition such that the eigenvalues and the eigenvectors are all real numbers. So the important thing is that the matrix A is real and symmetric. Okay, so given this fact, then you know that A can be decomposed like that. And what's going on with the big E here? So this is nothing else than the eigenvalues written as columns. Eigenvectors. And this matrix here has the accompanying eigenvalues on its diagonal, and zeros everywhere else. Okay? So if it's not symmetric, then you actually have to look at the inverse of the eigenvectors. Computing eigendecomposition is cubic again in the number of rows or columns of the matrix. So it's quite unfair that the standard matrix that's not symmetric sorry, that's not square. Does have a eigendecomposition. So generalization of an eigendecomposition is the so-called singular value decomposition, and this decomposition exists for every matrix X. So you have a matrix n by p, and then you can decompose this matrix X into these three matrices, U, S, V. U and V are matrices that are actually orthogonal. You see it here and here. And S is a diagonal matrix that has the positive singular values on its diagonal, and some of these singular values may be 0. So S is something looking like that. Probably some zeros here. Okay. And well, computationally, it's rather similar to the computational requirements for computing a decomposition of a square matrix. So finally, the concept of positive definiteness of a matrix. So looking at this number, so this is a scalar, you should convince yourself why this is true. So if this scalar for a symmetric matrix A is always bigger or equal to 0, then this matrix is called positive semidefinite. And if it's actually always larger, truly larger than 0 for all matrices, for all vectors that are different from the 0 vector, then it's called positive definite. And a positive definite matrix has full rank and therefore is invertible. And it also has the nice fact that all its eigenvalues are positive. And because all its eigenvalues are positive, from this fact you can again deduce that it's invertible. So this ends the rather short whirlwind tour through linear algebra. The concepts that were presented here are concepts that are always coming up in machine learning. So you should know those basic ideas. If you don't know them, try to find a book and restudy them.